Hi everyone, in this video we're going to go through 14C, finding the sample size. Basically what this means is we're finding n. So remember that n is your number of trials. So in the previous two sections with the binomial distribution, you were given n, the number of trials, p, the probability of success, and you had to find, and you were given a value for x. Okay, so how many trials did we want to succeed in? So in 14C, we're basically given information, but we have to find n. So with this example here, example 8, now I could go through it with you, but they actually go through it in the textbook. So I'm going to get the textbook up. And if you have access to the textbook, just remember that I shouldn't say a lot. Some of their examples have videos. So I'm going to play the video here and then we'll go through some other examples together.
This question here is a binomial question, but unlike others that we've done before, we don't know what n is. So we've got the probability of winning or the probability of success as being 0.48. Now the question asks us, what is the least number of games, i.e. what is n equal to, that must be played so that the probability of winning at least once is more than 0.95. So down below here, I've just defined my variable, let x be the number of winning games. Where x is a binomial distribution, we don't know what n is, but we do know that the probability of success is 0.48. So as I was saying, we want to know what the value of n will be such that the probability of winning at least once, there we are, x is greater than or equal to 1, be more than 0.95. Now the probability that x is greater than or equal to 1 means we're dealing with x equals 1 or x equals 2 or x equals 3 or x equals 4, but we're going to keep adding up all of those probabilities until we get to the total number of games played. Problem is with this is we don't know how many games we're going to play, and in fact that's what we're trying to find. So another way that we can express all of this is we can recognise that this is all of the probabilities excluding the probability that x is equal to 0. So the way that we can write the probability that x is greater than or equal to 1 is the same as 1, everything, subtract the probability that x is equal to 0. So all of this has to be greater than 0.95. To evaluate what the probability is that x equals 0, we can use the formula. So the probability that x equals 0 will be n choose 0 multiplied by the probability of success to the power of 0 multiplied by the probability of failure to the power of n minus 0, which will just be n. And that all has to be greater than 0.95. Still looks a little tricky to solve because we don't know what n is, but we do know that anything choose 0 is equal to 1. 0.48 to the power of 0 is also 1, and that's multiplied by 0.52 to the power of n. And we can use our calculator to solve from here, or we can rearrange and make the inequation a little bit easier to solve. Just watch that switching of sign through there when we multiply both sides by -1. Now you can solve this on your CAS calculator and you'll get n has to be greater than 4.58. Now given n is the number of games, it has to be a whole number. So we don't leave our answer as n is greater than 4.58. We say therefore the minimum number of games that need to be played is 5. Now a couple of other ways that you can go about solving this. One suggestion is to take the log of both sides. When we take the log of both sides, that allows us to pull this n value out the front using our log laws. And then to solve for n, I'm going to take that log to the other side. The thing you have to be careful though when you're using this method is whether or not you're going to change that sign around. Now it just so happens that log base e of 0.52 is a negative number. So when we divide by a negative number, our sign has to switch. In the end though, you would use your calculator to evaluate all of this, which gives us what we worked out before, n is going to be greater than 4.58. Another effective strategy that you can use is to plot the left-hand side and the right-hand side of this equation onto your graphics calculator. So you can see here that I've got my exponential 0.52 to the power of n coming through there, and my horizontal line at 0.05. Now we're looking for the region where 0.52 to the power of n is less than this horizontal line. So we want to look at the point where this curved line drops below the horizontal line, and you can see I've highlighted that in there. Now that intersection point is 4.58 that we've worked out several times before now. And so the n value, as in the integer that represents this curved line being lower or less than the horizontal line, will be n equal to 5.
All right, let's go back to the notes. So you can see all the working there, but in that video, you can see she solved it 3 different ways. In the working out here, we've got the log method. Okay, just taking note of the switch of the inequality sign. You could do it graphically, but the most straightforward way would just be using solve on your calculator. So you could just do 0.52 n to the power n is less than 0.05, and you're just solving that on your calculator. Question B, part B, I don't think she did on the calculator. So we're just going to talk through this one now. So I'll just go back to the question. What is the least number of games that must be played to ensure the probability of winning at least twice? So the first one was once, and this one is at least twice, is more than 0.95. So in question B, we're setting up the equation the same way. So we want x to be less than 2, okay, and we know because it's the we want x to be greater than or equal to 2, but when we're solving, we can say, all right, let's look at what we don't want, and we don't want anything less than 2. So what we have less than 2, let me just highlight it because I know you can't see my cursor. Values that are less than 2 are 0 and 1. So you can see that we've set up the binomial distribution in the next line using x equals 0 and x equals 1, because we want at least twice, okay, but that could go on forever. So we just take do what we don't want. So x is less than 2. All right, and that's equal to 0.05 because we do 1 minus what we have is the probability of what we don't want, so 0.05. Okay, so with the binomial distribution, you can see we've still got n here, which is what we're solving for. So the first term, we've got when x is equal to 0. So similar to what we did before, and we know that n choose 0, anything choose 0 is just 1. Okay, so this is equal to 1. Anything to the power of 0 is 1. And then we're just left with 0.52 to the power of n. So similar to what the lady showed in the video. Now the next part, we've got x equals 1. So we've got n choose 1. Now n choose 1 is just equal to n. So if I was to show you on the calculator, if you've whatever number here for n, so if we've got 10 choose 1, it would be 10. 20 choose 1 would be 20. Okay, so you can see that's represented by this n here. Then we've got 0.48 to the power of 1. So anything to the power of 1 just remains the same. So that's where the 0.48 comes from. And then we're just left with 0.52 n to the power of -1. Now, if you probably wouldn't keep going because n choose 0 and n choose 1 are consistent. Like that's a rule, I guess. Okay, so something important to put down. So now we've got an equation in terms of n, and then we can just do solve on our calculator. Sorry, I just paused to see what this little bit down here said. So you can see we've just used solve on the calculator. All right, so n equals -1 blah, blah, blah. Obviously, we can't have negative number of trials. So we've got n, it has to be, no, it's not solving for an inequality, but you can see here n is equal to 7.79. So n has to be greater than 7.7985, blah, blah, blah. So we round up to 8, okay, because we need a discrete number of games. So we've got to have 8 times. We can't also round down because it has to be greater than. So if you had a number that said 7.1, you can't round down to 7. It has to be more than that. All right, so let's do some questions. Okay, so there's, sorry, before we move on, the calculator instructions. So you can see there another method of using it. So you can use binomial CDF, and they've just got X for your upper, because we don't know what that is. Number of trials is X, but that's not going to work. Okay, but you can still follow these instructions. All right, so you highlight and copy the expression. So we copy the binomial CDF expression. You can see they've done that into the graphing screen. And then we tap on the table. Okay, so when we do some questions, I'll show you also how to do this on your calculator. And then you can just scroll down until you get a number that is greater than 0.95. And you can see there it is 8. So we get our integer values that way. All right, so let's have a look at question 1. So the probability of a target shooter hitting the bullseye on any one shot is 0.2. If the shooter takes 5 shots at the target, find the probability of missing the bullseye every time, hitting the bullseye at least once. So at this point, we know that n is equal to 5. Okay, so we're not looking at what n is. We're finding the probability. Let's just look at questions B and C to see when we're finding n. So question B, what is the smallest number of shots the shooter should make to ensure a probability of more than 0.95? And then question C, what is the smallest number of shots the shooter should make to ensure the probability of more than 95 hitting the bullseye at least twice? Okay, so we've got at least once and at least twice. Question A, you should be able to do, okay, because this is just straightforward binomial distribution. Where's my pen? Okay. So we've got n equals 5 and p is equal to 0.2. And for part I, we want missing the bullseye every time. So if you've got missing the bullseye every time, you don't need to set up a binomial distribution. This is similar to what we did in previous video. 0.8 is the probability of failure. Okay, so remember, probability of success is 0.2, so they have to add up to 1, so the probability of failure is 0.8. 5 shots, so it's going to be 0.8 to the power of 5. All right, I'll let you do that on your calculator. Part 2, hitting the bullseye at least once. So we want the probability that X is greater than or equal to 1. So that is equal to the 1 minus what we don't want. So 1 minus the probability that X equals 0. And then you can just do that on your calculator. So you can either do it as binomial CDF or a binomial PDF, depending on whether you wanted to do your lower limit 1, upper limit 5, or you could just do 1 minus X equals 0. All right, so 2 ways you can do that, and I'll leave you to finish that on your calculator so we can get stuck into question B. So for question B, what is the smallest number of shots? Okay, so we don't know what n is. All right, so that's what we're working out. We want the probability to be equal to 0.95, and we want at least once. Okay, so similar to the question that we did previously, all right, we can do 1 minus what we don't want, so 1 minus the probability that X is equal to 0. All right, and we want that to be greater than or equal to 0.95. All right, so let's just put the 1 over to the left-hand side. So then we're left with the probability x equals 0. Now, if I put that 1 over, I'm going to get negative 0.05, but just to counteract both negatives, then my inequality sign has to change direction. All right, so if we've got x equals 0, our probability of failure is 0.8 to the power of n. So basically, if x is equal to 0, that means, no matter how many shots I have at the target, I'm never going to win. So if I have 10 shots, it's going to be 0.8 to the power of 10. If I have 200 shots, it's going to be 0.8 to the power of 200. So we've just got to solve for n. All right, just before I move on, I just realized I shouldn't have the equal sign on here, and me being very particular, I want to get rid of it. Okay, so now we put that into our calculator. Let's move the calculator over here. So we can just do solve 0.8. One thing I didn't like about that lady in the video is I don't like it when people call the number 0 O, the letter O. It's a number. 0 is the number. It's not a letter. Okay, anyway, don't mind me. All right, so we get n equals, why does it always disappear? 13 point, well, it doesn't really matter what it is, 13.4. So n has to equal 14. So our answer, what is the smallest number? The smallest number is 14 games. All right, so for question C, okay, so I just tried question C and I kept making mistakes in my calculator. So I've decided to start fresh, which is quite frustrating. But I kept making errors on my calculator and I just thought, let's just start again because you don't want to keep seeing me make mistakes. So in question C, we want similar question, but we're doing at least twice. So we want the probability that x is greater than or equal to 2. So that's the same as 1 minus, I'm going to put this in brackets, the probability that x is equal to 0 plus the probability that x is equal to 1, and that has to be greater than 0.95. All right, I'm just going to, like I did in question B, just take that 1 over to the left-hand side. So I've got just left with the probability of x equals 0 plus the probability that x equals 1. Inequality sign changes, and we've got 0.05. Okay, so the inequality sign changes because you've got this negative here, all right? And when you want to get rid of it, you're dividing both sides by -1, and that gets rid of that negative. Okay, so x equals 0, we did that in the previous question, so I'm just going to quickly write that here. So that's 0.8 to the power of n. And then the probability that x equals 1, so if I write that as a binomial distribution, it's n choose 1, times the probability of success, which is 0.2 to the power of 1, times the probability of failure, which is 0.8 to the power of n minus 1. And that has to be less than 0.05. Now, at this point, we kind of can simplify it a little bit further. So we've still got the 0.8 to the power of n. Now, anything that is choose 1, so n choose 1 is just going to be n. If you had 10 choose 1, it would be 10. If you had 100 choose 1, it would be 100, and so on. So n choose 1 is just n. 0.2 to the power of 1 is 0.2. And then we've got 0.8 to the power of n minus 1 is less than 0.05. Now, I'm going to get my calculator out again. You can see all these attempts I had before. So I'm going to try it again. All right, maybe it was the inequality sign I didn't like. 0.8 to the power of n plus n, oops, times 0.2 times 0.8 to the power of, now I'm going to put n minus 1 in brackets. All right, just make sure my brackets are all good. So that is, and I'm going to put the inequality in. So less than, you don't really need to put the inequality in. Just use an equal sign. Then comma n, close your brackets, and then, oh, I get the same answer as before. All right, let's drag it down. Okay, so this is probably a good lesson because you might get something similar in your calculator. Let's just use the equal sign. Come on. Oh, I don't like it how it doesn't let me go across. Oh, so frustrating. There we go. All right, so I'm going to put an equal sign here now. See what happens. Okay, it's all right. I can deal with more than one solution. All right, so better. So using an equal sign was good. So previous question, I could use an inequality sign here. Clearly couldn't. All right, if only I did this in the video before I edited it. Okay, so what have we got? 21.7 blah, 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 blah. So we want 22 shots, which is the correct answer. Okay, so what I might also do is show you the other way in your notes. So let's just get the calculator up. All right, so what are we doing? Discrete, CDF. Okay, so your lower limit is 0. The upper limit we don't know. Number of trials we don't know. And the probability of success is 0.2. Okay, so we're just doing X and X, and it's not going to solve it. It's just going to say wrong argument type. Now we highlight that, and I'm just going to copy and then go into this screen here, paste it. No, that wasn't the paste button. Okay, I don't know why that doesn't work. Okay, let's just go up there now. Cool. All right, and tick. And we don't want to graph it, we just want the table. So go to the table. No, it's not what we wanted. All right, that's why it's a good idea to have instructions. So you can see the lower limit they had is 2. So let's go back and put 2 on the calculator. So I can just easily change that to 2. All right, and let's press the table again. All right, there we go. So I would just keep scrolling for X until I got, now what does it say? To view larger values, tap the XY. So tap this screen. All right, so we want to, so see how it says start 1, end. So let's go up to 30. We know what the answer is. All right, so now you've got more. The table's just become a bit bigger. So now we can see all the probabilities in blue, and we keep going until we get a number greater than 0.95. So there you can see it's 22. All right, so 2 ways you can do it. All right, let's scroll on to question 4. So Janet is selecting chocolates at random out of a box. She knows that 20% of the chocolates have hard centers. What is the minimum number of chocolates she needs to select to ensure that the probability of choosing exactly 3 hard centers is more than 10%? All right, so what have we got? 20%, so P is going to be equal to 20% or 0.2 as a decimal. We want the minimum number of chocolates she needs to select to ensure the probability exactly 3. So x equals 3. So it's not at least 3, it's exactly 3. Hard centers is more than 10%. So we want that to be greater than 10%, which is 0.1. Now I haven't done this yet on the calculator, but let's just see how we go. Just move my calculator over here. So this is a binomial CDF. So I might just go back to my main screen. Just clear that. All right, so interactive distribution of squared. All right, so x is 3, number of trials is n, and the probability of success is 0.2. Okay, doesn't work again, so let's highlight, copy. So copy, and then we're going to go to the graph. All right, we can clear what we've got there. We don't need that one. So we're going to paste what we've just had. Put that in. See if this works. Okay. All right, I'm guessing instead of n, I need to put x. That's probably where I went wrong. There we go. Beautiful. So we want the probability to be greater than 10%, so 0.1. So I can just keep going, and you can see that is at 7. So what are we doing? 7 chocolates. So 7 chocolates. I've eaten so many chocolates today. Just a little side note. All right, I haven't actually tried solve. Let's try the solve function for this because it is a little bit different. Let's just go back to main. So if we were doing this as a binomial distribution, we would have n choose 3 times the probability of success is 0.2, so 0.2 to the power of 3, and then times probability of failure, n minus 3, and we want that to be greater than 0.1. Now, we can do the combination on the calculator. You would think I'd probably check this before you weren't watching me, but this is why it's probably a good idea to be confident with your calculator and explore it. So advance, so we want n first, which is what we're solving for, and 3. Okay, so I'm just going to not press enter because it's not going to do anything. So let's go back up to, solve. All right, so I might just put that in brackets because brackets are our friend. Okay, so times 0.2 to the power of 3 times 0.8 to the power of n minus 3, and I'm going to use equals 0.1 comma n. Let's see if it works for us. It's got it in terms of factorial. Let's just see if we can, yeah, it's got the factorial in there, which is a bit annoying. Okay, so you would, a question like this, just do graphically like on the table, sorry, like I just showed you. Okay, so moving on to question 5, sorry, it's going to be an extremely long video. The probability of winning a prize in a game of chance is 0.35. So let's write that down. P equals 0.35. What is the fewest number of games that must be played to ensure the probability of winning at least twice is more than 0.9? So we want the probability that x at least twice, so greater than or equal to 2, is more than 0.9. All right, so I think it's a lot easier just to do that on the calculator using the graphing screen. So let's just do that again. So interactive, discrete. This time we're CDF because we're going to be doing 2 and above. So the lower limit is 2 because we want to be greater than or equal to 2. The upper limit we don't know, and remember use x. So before I made the mistake of using n, and the probability of success is 0.35. Go OK. It's not going to work. All right, you get the error message, but that's all good. We just want to copy. So copy and then go into your graph and table, clear what you've already had there, and we just want to paste what we just put. Okay, so put that in, tick, and then go to table. And what do we want? 0.9. So we're going to just scroll down to 0.9. So it's going to be 10. So 10 games. All right, so I think that's a lot easier than doing the solve, especially when you saw me making those errors before. I'm quite liking that other method. All right, question 7. Monique is practicing goaling for netball. She knows from past experience that her chance of making any one shot is about 70%. So that's pretty good. Better than that other netball player from that other question. Her coach has asked her to keep practicing until she scores 50 goals. How many shots would she need to attempt to ensure that the probability of scoring at least 50, so the probability of X is greater than or equal to 50. Oh, wow, 0.99 is more than 0.99. Okay, so again, let's just do that on the calculator. You can just go straight to here and change your values, okay, because we had binomial CDF before. So instead of being, I forgot a 0 there, that had to be 50, not 5. Go back to the calculator. So your lower limit is 50, and then you can keep x because x being our upper limit and x our number of trials, and probability of success for this one is 0.7. Okay, so then we can just go to the graph, the table. Oh, why have we got an error? Actually, you're going to have an error because all the way up until we get to 55. So we're starting at 1, ending at 30. So we need to just start at 55. And let's go up to 100. Okay, so that's just going to be a little bit quicker for us. All right, well, you want to keep going until we get above 0.99. Going to eventually get there. All right, so it is 86 shots. Or 86. Or shots, because she's not always going to get a goal. Okay, so that's a 0 there. Okay, so using that graphing screen and the table is a lot easier. All right, and that's the end of the video. So girls, some good questions for this one. So if you think you need to have a little bit more practice, do some questions from the textbook. All right, bye.